I was asked to present on some of the physics and technology involving inertial confinement fusion and kind of the story of how we got to ignition. So that's what I'm doing. Thank you for the invitation. Yeah, I'm sorry I can't be at UCLA. It would have been fun to visit my alma mater again. Let's get started. Okay, the Greenhouse George event was the first time actually humans ignited thermonuclear fuel. This happened in 1951, but it used the largest atomic bomb ever fielded to make this happen. This was the proof of concept of thermonuclear ignition and fusion. We created a star on Earth for a brief moment, and in the declassification document, the quote is the first thermonuclear test explosion, and it burned well. So you guys you're at a fusion conference. Uh, so I'm actually getting feedback again. That was fixed for a moment. But anyway, you know that many scientists involved in fighting the Cold War were actually also interested in controlled fusion for non-destructive purposes. And the fusion programs with the goal of laboratory-based ignition were actually declassified in 1958 in the Atoms for Peace program. There are some concepts related to fusion that still remain classified even today. Okay, but nevertheless, despite decades of work, ignited thermonuclear processes only occurred in nuclear weapons testing and stars until 70 years later, where in August 2021, humanity again ignited thermonuclear fuel in the laboratory, this time using the National Ignition Facility. So what you see in the center of the screen here is the National Ignition Facility. The, you, the target chamber is here on the right. You see two target bays uh, 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 that join up to the target chamber. They're fed with electrical energy that enters through these capacitor banks on the sides of the facility. The whole thing has the footprint of about 3 football fields laid side to side. So 327 megajoules of electrical energy is stored in these capacitor banks. The laser light is generated using flash lamps and then directed toward the target chamber. By the time the laser energy gets to the target chamber, we have 2.2 megajoules of 351 nanometer, what we call blue light, and that's what we shoot the ICF targets that we field with. This whole thing took 20 years to design and build, and after it was built, it took another 10 years to actually get to ignition, which wasn't originally in the plan. So I like to say we now have existence proof that ignition is possible in the laboratory. But of course, this has been extremely difficult even after getting the facility built. So this is a plot of fusion yield in kilojoules versus year. I'm showing eight, or actually seven, of the key steps it took for us to get from something that didn't work back in 2012 to where we are today. In fact, we actually did 24 different projects or campaigns. This only shows kind of the seven that were kind of key to getting to a burning plasma ignition and target gain. So back in 2012, we had a target that was designed to actually achieve high gain. It didn't work, but this period was important for creating all the diagnostics and simulation infrastructure and target production that we needed for the future work, and also implementing or learning how to do laser operations. But there was a political consequence to this, what was regarded as a failure, and we had to recover from that to make further progress. So the progress you can see, this is log scale, but you can see it kind of happened in steps. And in a way, it was kind of regular, almost quasi-steady. So we first started to address problems with ablation front Rayleigh-Taylor instability and something called reduced coast time. I'll get into the details of what these jargon terms mean throughout the talk. But we were able to make some fairly rapid progress from this initial recovery, increasing fusion yields by about a factor of 20. We achieved something called self-heating and fuel energy gain, where we got more fusion yield out of the fusion fuel than we put in. We then started to improve our laser plasma instability control, increase the velocity of our implosions, improve symmetry control, and we kind of hovered around the threshold of burning for several years. And then we finally realized that if we make our system a little bigger by increasing the capsule mass, a little more symmetry control, and a little more capsule quality, we'll talk about those in a minute. We're able to get to a burning plasma, ignition, and target energy gain, where we're getting more fusion yield out of our target than we put into our target in fairly short order. This is like a period of 2 years here. And we continue to try to extend our progress, of course. You can read about the details of these in these physical review papers that were published in 2024. Okay, so today's target design was built upon a 10-year evolutionary exploration of how to manage all the technical challenges. So if I go back to this target chamber here is 10 um, meters in diameter. In the center of that is our fusion target, and that's what I'm showing here. So this is a just a drawing of our typical target geometry. What we have is a metal can that we term a Hohlraum, which is a German word for hollow room. It actually serves an X-ray converter. Laser light actually hits the inside of that can and converts to X-rays. And inside the center of the can is a capsule made of low Z materials, and there's fusion fuel in a cryogenic state layered on the inside of that capsule. So that's our stereotypical, what we call indirect drive inertial fusion target geometry. And you can see we've evolved through a bunch of different designs, but often you basically have to be an expert to see much of a difference. They're basically small dimensional changes over that period of a decade of work to try to improve the fusion performance. The one that's obvious is we made the target a little bigger and the capsule a little bigger. But other than that, these are very subtle changes that occur in the target geometry that were part of making progress from going from failure to ignition. On the right, you see laser power versus time. This is more obvious, or this reflects a more obvious set of changes that took place as we evolved through these different target geometry changes. And I've labeled these laser pulses to kind of match up with their accompanying target here on the left. So the initial laser pulse was shown in blue here, where we have a relatively long laser pulse at about 22 nanoseconds duration. And you see there are a lot of structure to it, lots of changes in laser power as a function of time. What we learned is we had to start making those laser pulses shorter, and we had to start adding power earlier in time uh, in order to better control hydrodynamic stability of our implosions. The shorter duration actually helped with symmetry control of our implosions. We'll get into the physics of that later. And you can see the structure that was present in the initial laser pulse starts to go away as we evolve towards essentially simpler laser pulses that actually end up giving better performance. So there's less structure in these laser pulses, and there's a trade-off when we do that, having to do with the amount of compression we can get out of our implosions, and we'll talk about the physics of that. And then finally, we increase the duration of this period of peak power, and our jargon term for that is reducing coast time. So the upshot of this is the qualitative design of the ICF targets that succeeded in getting ignition were actually unchanged from the 1990 era concepts. And there's a famous paper by John Lindell in 1995. But the tactics that we needed to get things to work, to go from failure, which is, this was failure here, to go to something that succeeded, required many small changes. And what is characteristic of ICF systems in general, ICF systems have extraordinary sensitivity to small changes. And that's one of the challenges with computation, which I think is what your conference is about. We have a very difficult time predicting behavior because of just the innate sensitivity of these systems to small changes that, to an average person would be insignificant. Okay, so we use the laser pulses in the target geometry to control a lot of aspects of what the fusion fuel is experiencing, in particular compression and heating. And in this slide here, I'm trying to illustrate kind of the key levers that we use to control ICF implosions. I already mentioned the laser pulse on the previous page, and the laser pulse here is shown in blue. This is in terawatts versus time, power versus time, and time is in nanoseconds. And here's the structure again that we talked about in the laser pulse. And I'm pointing out three key parts of the laser pulse that actually have leverage on controlling uh, the fusion fuel. The early time part of the laser pulse ends up being responsible for the hydrodynamic stability of the capsule fuel system and the entropy of the fusion fuel. And our jargon term for that is adiabat, which is a measure of entropy and a measure of compression. This peak power period is actually responsible for the velocity that our implosions obtain. And kinetic energy is important for the way ICF systems work, so velocity is important. And it turns out this last period, how we turn the laser pulse off and when we turn it off, our jargon term for that is coast time, but it's connected to the mechanical transfer of power or mechanical generation of power as kinetic energy is transformed into internal energy. Okay, the geometry of the target is basically responsible for controlling symmetry. So again, here's our hull ROM with the far end lopped off. Here's our capsule with our fusion fuel inside. Laser light again comes in and hits the inner wall of the hull ROM, not the capsule, where we point the laser power and how much energy or power each one of these beams carries will influence the symmetry of the capsule inside as it absorbs X-ray energy and implodes. In addition to that, we have gas fill inside the hull ROM, generally helium, that is essentially provides a back pressure on the plasma that's generated by the laser light hitting the hull ROM wall and causing it to expand. And by engineering the gas fill, the laser pointing, and the laser power, we have some hope of trying to control the symmetry of the way the outside surface of this capsule explodes in response to X-ray absorption and then implodes the fuel. The pressure that's generated on the outside of this implosion is related to what we call the radiation temperature to a high power. The radiation temperature is kind of like a color temperature, and that's shown in red here on the left. It's somewhat sympathetic to the laser power versus time, but the hull ROM tends to damp out rapid oscillations in time, and so the radiation temperature has less structure than the laser power uh, does. But it's the radiation temperature that actually drives the pressure on the outside of this capsule. So the pressure, the changes in radiation temperature correspond to changes in pressure on the outside of the capsule, and that's what drives the capsule inwards upon itself. Okay, so there's a lot of engineering associated with these targets. That generally you don't have to worry about in magnetic fusion. You just put the fuel inside the device, and the device is the thing that's engineered. But our targets are part of the plasma creation process, and of course, these targets become plasmas themselves. These are highly engineered objects. They're small, so this is the dimension here, 1 centimeter in height. That's the hull ROM, the gold hull ROM here in the middle. These are arms that we actually cool the target with to get it to cryogenic temperatures before we do our experiments. Here are the laser entrance holes on the top and the bottom. You can see there's a lot of engineering involved in this target. In the center of that hull ROM is the capsule. The capsule in general is about 2 millimeters in diameter, and the thickness of the wall of the capsule is on the order of actually 70 to 200 microns thick. And the thickness of a human hair is about 100 microns, so that gives you some idea of what the scale is. On the inside of that capsule is a cryogenic layer of DT ice, and generally in a lot of our experiments, the thickness of that ice is 50 to 65 microns, so about half the thickness of a human hair. So this capsule material, we also call it the ablator. is generally made out of materials that are low down on the periodic table. So we use a high density carbon, for example. We call that HDC. We use plastics, and plastics are basically carbon and hydrogen. In particular, we use a glow discharge polymer type of plastic. We use beryllium, boron carbide, and things like that. These are materials that are compromised between their ability to absorb X-rays, which is important for X-ray driven in ICF, but also generate high pressures. Because of this, these all have to be made. They're man-made. They're not perfect. So because they're not perfect, defects often show up in all of these objects, and these defects influence the performance of our fusion experiments, and they can be quite damaging and frustrating because, as I said before, ICF systems are generally extremely sensitive to small changes. So some of the defects we've seen in the capsule construction are surface pitting on the outside of these capsules. Of course, we want them to be perfectly smooth. Of course, you can't make them perfectly smooth, so we do get pits. In the through thickness of the capsule material, you might actually have voids. There's also structure in some of these materials. If you don't have an amorphous material like carbon, high density carbon, it's basically crystalline. Similarly, beryllium is crystalline. You have crystal structure inside of the through thickness of this material on the scale of tens of microns or submicron scale, depending on what type of structure the engineers were providing. And these type of deviations from like a fluid plasma physics picture tend to create uh, uh, seeds for hydrodynamic instability, which then ends up injecting high Z material into our fusion fuel, and we try to make it hot. And you can actually see in imaging of our heating fuel bright spots coming out, which are indications of instability generated by these features, flinging kind of mid-Z material into the deuterium tritium fuel when we try to make it hot. And of course, X-ray emission means we've lost some energy. Okay, so the Hall-ROMs, um, the way they work is, again, they take laser light and convert it to a bath of X-rays. So again, here's our stereotypical indirect drive target, a Hall-ROM, which is a high Z metal can, usually gold or uranium or a combination of gold and uranium with a capsule inside. The laser light hits the inside wall of the Hall-ROM, and energy is absorbed by that material through inverse bremsstrahlung, where the laser frequency matches the electron plasma frequency of the material. Some of that laser light is redirected by laser plasma instability through scattering processes such as Brillouin and Raman scattering. But most of the laser light usually is absorbed, and that creates a bath of X-rays. The bath of X-rays are then incident on the outside surface of that capsule, causing that capsule to explode as it absorbs that X-ray energy, and it generates a large pressure. And that pressure is actually what drives this capsule inwards upon itself. And because there are jumps in pressure, we also generate shock waves that travel through the material and the fusion fuel that's on the inside. But it's that pressure that accelerates the whole thing inwards upon itself. So you can figure out the scaling for how the ablation pressure is generated just by balancing sigma t to the fourth, the X-ray power that's entering into the surface of the ablation front with the mechanical power of that surface expanding in response to absorbing that energy, expanding at the sound speed, for example. And that allows you to solve for the ablation pressure. You find out that the ablation pressure is related to material properties like the atomic number and the atomic mass, and again, the radiation temperature to the 3.5 power, and a measure of how much of that X-ray energy is rejected by albedo effects. So as you try to put energy into this system, some of that energy is just reflected away, and we call that the albedo. The pressures that we generate using these ablator materials is generally on the order of 100 to 200 megabars. So that's 100 to 200 million atmospheres is what we're squeezing this capsule and fusion fuel um, up with. Okay, so here's kind of a cartoon of how the whole system works together with the target and the laser. And now I'm going to try to tell you what an implosion is. So here's our hull ROM with the capsule inside. We have the laser energy coming in through the top and the bottom, hitting the inside wall of the hull ROM. And as I said before, we're putting in 2.2 megajoules of laser energy with the NIF. The laser energy is converted to X-rays, and this creates an X-ray oven that is absorbed by the capsule. The capsule starts to ablate, explode in response to receiving that X-ray energy, and you're creating 1 to 200 megabars of pressure on the outside surface of that capsule, and it starts squeezing up. Because the surface area of this capsule is small compared to the surface area of the hull ROM, uh, you don't get the full 2 megajoules of laser energy absorbed into the capsule. You only get a small fraction of that, generally about 1/7 to 1/10. So it's typical these days we're absorbing about 250 kilojoules of energy that entered into this hull ROM. And it's just the ratio of surface areas of the capsule to the hull ROM. Okay, as I said, we generate a large pressure here that squeezes this capsule up. Because it's a spherical system, it runs out of anywhere to go. We call this the implosion, and we're accelerating the capsule with the fusion fuel up, and it's uh, generating kinetic energy. And as we squeeze down the volume, we're doing PDV work on the fusion fuel inside, and that is the implosion phase. Eventually, it runs out of anywhere to go, so all of that kinetic energy that's been acquired in flight uh, stagnates at the middle of the implosion, and we get about 20 kilojoules of energy into the fusion fuel. Now, this is like another order of magnitude lower than the energy absorbed by the capsule, and that's because most of the energy absorbed by the capsule was expended creating these plasmas that accelerated the capsule and fusion fuel inwards upon itself. So it's kind of like putting a rocket into space. Most of the rocket doesn't get into space. Most of the rocket is consumed trying to get a small payload of a satellite into space, and our system works the same way. So this final phase we call stagnation. So we are knowingly sacrificing a lot of energy in order to amplify pressure, it turns out. And that's because the fusion fuel essentially follows a PV to the gamma sort of law, where as we shrink down the volume, the pressure goes up, and we result with a final pressure of about 600 or many hundreds of gigabars. So many hundreds of billions of atmospheres of pressure, and that's the whole purpose of an implosion. So you sacrifice energy to make pressure. Okay, so I'm going to show you kind of a PR cartoon movie, but this actually illustrates this process pretty well. So here's the laser light. You see it's red here. That's because it doesn't damage the optics as much as blue light. As the laser energy is approaching the target chamber, it's converted for a moment to green light, then to blue light. Then our target is at the center of the target chamber. Again, we're shooting at hull ROM, so the laser light enters the top and the bottom, and the laser light hits the inside wall of the hull ROM, making X-rays. The capsule absorbs the X-rays, explodes, and the equal and opposite reaction implodes the what's left of the capsule and the fusion fuel inwards upon itself. So this is, again, kind of like a PR movie, but it actually illustrates the process pretty well that I was trying to talk to on the previous slides. So, all right. So more mathematically, the way the implosion process works, and to hopefully help you understand the pressure amplification nature, you can write down basically Newton's laws for a shell of material. You have a pressure on the outside, pressure on the inside, radius of that shell, and that shell represents the fusion fuel and whatever mass of the ablator is left after being turned in, after the outside surface is turned into plasma. So you can write down a trajectory equation for that shell. Again, it's mass times acceleration equals force. The difference in forces on the inside and outside is just pressure times the surface area. We are consuming the outside of the ablator by turning it into this exhaust, rocket exhaust. So mass is consumed as this thing implodes. And then you need a statement of thermodynamics for the pressure inside. As I said, PV to the gamma constant is reasonable, although the actual equation is more complicated. We'll get to that later. So the trajectory of the capsule, basically it sits at large radius. This is the center plot is the trajectory of the capsule. The capsule sits at large radius, absorbing X-ray energy, and then it ablates and it races inwards and achieves a small volume. The outside of the capsule, we're generating these pressures from the laser interacting with the Hall-Raum, again on the order of hundreds of megabars. The pressure inside the capsule is negligible at early time, but as the implosion proceeds, the internal pressures increase very rapidly, eventually surpassing the outside pressures. And there's a moment here where the pressures inside and outside are equal. That is a moment of free fall, and that we call that the radius of peak velocity. And after this point, the implosion has so much kinetic energy that the internal pressure doesn't just arrest it. The internal pressure is resisting the implosion, but it continues to climb because it has so much kinetic energy that it continues to squeeze up the volume. And eventually we create a pressure amplifier. So we've increased the pressure we've increased the pressure on the inside of the capsule compared to the outside of the capsule by about a factor of 4,000 by using an implosion. And all implosions basically work this way. So this radius of peak velocity is kind of important because the physics of this system says you want to bring as much kinetic energy to as small a radius as possible in order to amplify the pressures as much as possible. And our jargon term for that is making the coast time short. You don't want the implosion to coast, otherwise the internal pressure kind of pushes back on it, and you won't achieve as high an internal pressure. So we found this in experiments very early on after the initial failure of the National Ignition Campaign. Here's a plot of laser power versus time. Again, we're playing with the pulse shapes. Traditionally, we would have thought that if we increase the laser power as compared to like some baseline case, we should get better performance. But what we found in these experiments, if we actually extend the duration of laser power, keeping without actually increasing the power, we actually got better performance in terms of the pressures that were generated at the center of our implosions. And the difference between that when that laser power ends and the peak time of energy generation of our implosions, that is what we literally call the coast time. So if you look at the pressure that we infer from our experiments versus that coast time, the color code here corresponds to these different laser pulses. We had our baseline case, we had the high power case, and then we had the lower power, longer duration case. And we found early on that, again, if we reduce this coast time, we get a very rapid increase in pressure inside our fusion fuel. And we understand the theory for this years later. And you can see a computer model also showing that response to reducing the coast time. But you also see the computer model predicting that we should have gotten ignition and the pressures inside would have just kept going up exponentially. And in fact, in reality, this was not the case. The pressures did go up and follow the computer model for a while, but eventually computer models and reality diverged. And this is one of the challenges we faced in the subsequent years. But we did learn from this series of experiments that it was important for us to try to keep this coast time short compared to the time it takes that Hall-Raum to cool off after the laser drive is off. Okay, so I'm focusing on pressure a lot, and I want to just kind of remind people why I'm focusing on pressure a lot. And that is because what we're trying to achieve here with our thermonuclear fuel. So ignition is this particular process where we obtain a thermonuclear instability, and it's only possible if we have two things going for us. We know if you look at the reaction rate for deuterium-tritium, which is our favorite fusion fuel, that as we increase the temperature, the reaction rate goes up. So imagine putting in some heat to make the temperature go up. then the reaction rate goes up and you make some DT fusions. And DT fusions, as everybody in this audience knows, makes neutrons, which is 80% of the energy, and alpha particles, which are 20% of the energy. Okay, so in our case, we are trying to thermalize the alpha particles. So we have a plasma of deuterium and tritium. Uh, uh, that is our fusion fuel. And as fusion occurs, these alpha particles are generated and they can run into the plasma and thermalize off the electrons. The thermalization you have a higher chance of thermalization if the density times size of your system is large enough. So in our case, about 0.4 grams per centimeter squared. So if we have a high density or a high radius, large size, or preferentially a product of those two that's high, then we have a high chance of thermalization. If we thermalize the alpha particles that are generated with fusion, we can cause the temperature of the fusion fuel to go up. So, uh, so the temperature of the fusion fuel goes up, we get more reactions. If we get more reactions, we get more alpha particles. If we can thermalize those alpha particles, we can get the temperature to go up again. And we're trying to actually generate this feedback mechanism where more reactions create more heating. And that requires a large product of density, radius, and temperature. And so, of course, density and temperature is pressure. So that's why pressure is so important for trying to achieve ignition with an inertially confined fusion system, because that's key for generating thermonuclear instability, which is what we're trying to do. So we're trying to create a situation where you get a thermal runaway that creates just an exponentially large number of fusion reactions and exponentially large increase in temperature. And that's how we make our energy. So this requirement on rho r, areal density, and temperature kind of set a requirement on energy for an ICF system. So imagine a ball of deuterium and tritium that we're trying to ignite, some radius r. The ideal gas law applies to a hot DT plasma. So the pressure in the plasma is related to the atomic number, atomic mass, and the temperature and the density. So internal energy is 3/2 PV. If you combine these together and then you uh, put in just a spherical volume, you find after just a short amount of algebra that with a fixed rho r, which you need for thermalizing alpha particles, and a fixed temperature, which you need for alpha heating to actually exceed Bremsstrahlung losses, that the energy required to get to ignition goes as 1 over the density of your system squared. So if you are limited in energy, you need a very high density. Otherwise, there's no way you're going to achieve ignition. If you have a large amount of energy, say with how I started this talk, you have like the largest fission bomb that's ever been fielded, then you don't need as much compression. This is why, ignition was achieved in the 1950s using bombs, but took us a lot longer to achieve in the laboratory, where we're much more limited in energy. So for realistic energies that we can achieve in the laboratory, we really do need an implosion to try to create as much compression as possible to try to drive this density up as high as possible. Otherwise, we have no chance of achieving ignition. Okay, so let's look at that in a little more detail. So we have this ICF system, which we're showing here on the left. This is simulation showing density on the left half of the image with actually realistic perturbations to that shell, to that ablator and fuel coming from the target fabrication features that we mentioned earlier. On the right of this figure, you see temperature. And there are key processes fighting for control of what's going on in this fusion fuel as we're doing these implosions, trying to get the pressure up. You have alpha heating, which is, of course, what we want. And in terms of power per unit mass, that goes as density to a high power of temperature. We have Bremsstrahlung losses, which are trying to cool off our plasma. That goes as density as the square root of temperature. We have thermal conduction, which is taking heat from the hot central core and taking that energy and diffusing it outwards to the shell. And actually, as that energy leaves the center and hits the cold fuel surrounding the hot center, mass is returned into the fuel. So we're actually creating what we call a hot spot in our ICF implosion on the fly. This hot spot in the middle doesn't come from the gas; it comes from that ice that we started with ablating into the center. Okay, so you can write a heat balance equation for this system where the time rate of change of temperature, knowing that the heat capacity of deuterium and tritium is 115 megajoules per grams per keV, is a power balance between alpha heating, how many alphas we stop in the hot region, and the losses due to Bremsstrahlung and electron conduction, who are trying to take energy away. And of course, we have the key way we have of putting energy into our system, which is PDV work, where on implosion, we're squeezing this thing up and we're doing PDV work on the fuel and heating it. And as I said here, we actually ablate the DT ice from the inside out, and that's how the hotspot mass is generated. And more than 90% of the mass in the center that actually ends up igniting comes from that process. Okay, so as we squeeze this thing up during the implosion, where the radius is rapidly shrinking, and we're traveling at velocities on the order of 350 to 400 kilometers per second, we're heating the core up through PDV work. But because this thing eventually runs out of anywhere to go and explodes, the same term that heats up the fusion plasma actually cools it. And this is different than magnetic fusion, where you generally only have to worry like Bremsstrahlung and electron conduction losses. In ICF systems, we now have to worry about the same physics that heats our plasma, taking energy out of our plasma through kind of a refrigeration effect. It's the expansion of the volume if we don't ignite in time. So as a result, ICF systems are different from magnetic systems in the fact due to the fact that we're highly impulsive. So we just have this brief period, and here what I'm showing is the power balance from solving these differential equations as a function of time. We're looking at power in gigajoules per second. We have a short period where we can get alpha heating to be positive and potentially outstrip the cooling terms of electron conduction and Bremsstrahlung losses. PDV work, as I said, helps us on implosion, the adding to the heating, but actually hurts us on explosion because it takes energy out. So we have a very brief period here in time where we have a chance of engineering that thermonuclear instability that's required to generate ignition and high yield. So from that power balance, we can define some milestones that we actually have passed in our work. One is a burning plasma where the alpha heating in integral exceeds the amount of energy injected into the system through PDV work. This is similar to the metric that people in magnetic fusion work, except in magnetic fusion use. But in magnetic fusion, you have these external sources of heating that go into your plasma. In an ICF plasma, the only source of heating is this PDV work, but it's the same sort of physics definition of a burning plasma that MFE people use. So thermonuclear instability, which is again what we call ignition, occurs if we've engineered a situation where all of these cooling terms are negligible except for the alpha heating term. And again, the alpha heating term goes as a high power temperature. So essentially, if you've engineered this situation, you get a Riccati equation where the time rate of change in temperature goes as a high power of temperature. This is thermonuclear instability. The time scale over which this occurs is tens of picoseconds in an ICF system like ours, and we call this the bootstrapping time. So we have to arrange this situation and get this thermonuclear instability to take place before the whole system blows apart. And so that's what we've been able to do. So we have these different metrics, burning plasma ignition and target gain. They all mean something different. The ignition boundary we know for magnetic fusion is determined by the Lawson criteria, which is a product of density, temperature, and time. For an ICF system, we have a similar sort of Lawson sort of criteria, but again, because of the impulsive nature, you can't use the exact same criteria for Lawson's criteria for ignition between ICF and IF and magnetic fusion because of the impulsive nature. So here, these dash curves actually show the Lawson criteria for ICF system, taking into account the impulsive nature and the fact that it blows itself apart. And you can see our history of data where we struggled for years approaching that boundary, but then we were eventually able to break through. And this is pressure times time, pressure times confinement time versus temperature. You can see once we hit that Lawson boundary, we get an explosive increase in temperature, which is, again, what ignition is. It's this thermal instability. If you look at another plot, this is target gain. This is the amount of fusion yield that we've generated as compared to the amount of laser energy that went in. I'm plotting this versus laser energy. You can see our kind of early struggles until we were finally able to get enough energy into our system where we got to a burning plasma. Then we ignited. This is where thermal instability takes place. And then a little bit later, we passed the point of scientific break even where the fusion energy coming out now exceeds the amount of laser energy going in. And we've been operating in that regime ever since. And again, this was like a decade of work to try to incrementally get through these different periods. Okay, so I've mentioned rho R a lot. Here's going to show up again because one of the other considerations that's important for generating fusion energy is how much of the fusion fuel you've burned. Um, for us, how much fusion fuel we burn is basically a race against time because you basically, the statement of how your burn fraction, which is the fraction of fusion fuel burned compared to how much fusion fuel you started with, is just completely determined by how much fusion yield you can generate before the system blows apart. So here's our stereotypical implosion. We have a shell of material with the hot spot of burning fuel inside. The fusion yield rate goes as a product of mass, density, and reaction rate. Since the burn fraction is just a ratio of how much you burn compared to how much you started with, all we need is a dynamic time, which comes from Newton's law. The time to blow apart is related to the rho r of the shell, how much inertial confinement you have, the size of the system, the radius, divided by the pressure that's generated inside. So the higher the pressure, the faster it blows apart. Uh, the smaller the areal density, the faster it blows apart. The higher the areal density, the slower it blows apart. And the larger the scale, the slower it blows apart. So you can use this to come up with a scaling for the burn efficiency. It's basically just the density, the reaction rate, and this time. And that says that the burn efficiency is just a function of the root mean square of the shell areal density, the hotspot areal density, the reaction rate at the characteristic temperature, and essentially a sound speed, square root of temperature. And you see from our data, we have a pretty good correlation between that burn fraction formula and the burn fraction we actually measure in experiment. So you see that's actually, in our case, we've actually been able to achieve about 12% burn efficiency. And we hope to improve that further. Improving that burn efficiency more requires increasing the areal density of our system or the size of our system. And so that's kind of the path we're on. So I've mentioned rho r now several times. It's come up a lot. Um, I also mentioned at the beginning how things just didn't work. Because of this burn efficiency formula that shows that you get higher burn efficiency with higher rho r, the early experiments on the NIF actually targeted very high rho r because we thought we were just going to get ignition and we wanted high gain and we wanted high burn efficiency, and that seemed reasonable. But experiments did not agree with expectations. So I'm showing here on the left an interesting plot of fusion yield versus the energy into the DT. We call that the fuel gain, how much energy you make with fusion as compared to how much you actually put into the fusion fuel. And I'm showing in apricot color our history of experiments. And in blue, I'm showing our database of simulations, about, I think it's 17,000 simulations that were generated for various conditions. And you can see, of course, the simulations agree with our theoretical expectations that the very highest levels of fuel gain occur at highest levels of fuel rho r, areal density. And so the original experiments on the NIF targeted this region here, where you're going to get the highest performance. But when experiments started, you can see there was actually a complete disconnect between what we were observing in the laboratory and what our expectations were from simulations and from theory. So we actually had to make a strategic choice, and our strategic choice was basically to back off in areal density, back off in rho r, to try to get to a place where simulations and experiments agree. Because if you're out here where simulations and experiments don't agree, you can't use these simulations to figure out what to do next. We call this strategy the base camp strategy. It was difficult for a lot of people to accept because backing off in rho r meant backing off on what people thought was the most important thing for ignition and energy gain and burn efficiency. Um, but it had to be done to try to find consistency between our simulations and experiments. And eventually we were able to, uh, again, navigate our way to higher fusion performance, although we're still not back to the ideal highest performance that is possible. So the strategy of backing off was pretty critical for our program, but it did mean we sacrificed high levels of fusion gain theoretically and high levels of burn efficiency theoretically, but it was necessary for our success. Now, this discrepancy here, is very significant, and it's kind of very striking how at lower levels of rho r, we actually have such good consistency, and at high levels we don't. We still don't understand the reason for this discrepancy, and we're still trying to understand it to this day. But we do have some hypotheses as to why this discrepancy exists, and these hypotheses wrap around some of the challenges we've been facing ever since we started work recovering from the National Ignition Campaign. So the hydrodynamic instabilities generated by these defects in the capsules and just by the nature of Rayleigh-Taylor um, are one of the key um, uh, hypotheses for why that discrepancy exists and why we continue to have struggles. And some of our tactics over the last 7 years have actually tried to address this. So you have, this is a plot of ion temperature and density, showing what is kind of supposed to be our stereotypical implosion, where we have a shell of material with a hollow inside. We're supposed to squeeze this up and get a hot core in the middle and have a nice shell on the outside. But because of this amplification nature of implosions, Rayleigh-Taylor instability is amplified just as much as pressure is amplified. And so we struggle to maintain this nice spherical shape in time on many of our implosions. And the hot core in the middle wants to trade places with the cold material out on the outside. And this leads to a flinging through some of these jets. I'm going to show you an experimental movie here, a flinging of blader material into our central hotspots. And of course, since the deuterium and tritium is basically hydrogen, when you fling higher Z materials into that hot hydrogen or those hydrogen isotopes, it tends to increase the radiation greatly. And when you increase the radiation, you throw away energy. And as I told you earlier, energy is pretty important because for an ICF system, we have to go to these extreme means of getting high compression because we get so little energy into our fusion fuel because we're trying to use an implosion system to make these things work. So energy is precious, and we can't afford to radiate energy away. The other physics that we've struggled with that is probably related to that discrepancy on the previous page is asymmetry. Here, this looks perfectly round to your eye. This is a plot of mass density showing what is a spherical implosion. As you do the implosion, we tend to struggle with symmetry control, and the implosions often change shape, and the mass in the shell tends to migrate to certain locations. And again, if you look at some of our data, this is a experimental uh, neutron image, which we call this a downscatter image. It's fusion neutrons, 14 MeV neutrons generated in a hot spot, hitting the cold fuel and being scattered towards the detector. And that shows us the shape of the fuel around the hot spot. And you don't have to be an expert to see that this isn't round. There are thick spots and there are thin spots around the side as you go around an azimuth. So it's not a perfectly round implosion. It turns out, again, both of these type of processes of instability and mixing and asymmetry cost us energy, and we can't afford to lose a lot of energy. So hydrodynamic instability, of course, people in magnetic fusion have to deal with hydrodynamic instability all the time as well. Anywhere you have density gradients and pressure gradients in opposition, Mother Nature likes to change places of those materials. And this can be pretty catastrophic for inertial fusion. So again, here's the movie that goes with that previous slide where you can actually see how quickly this develops. You already see some structure here on the outside of the capsule, but let's just watch the movie. So you saw here for a moment, it kind of looks like things are developing properly. We're developing our hot spot inside. We have a cold shell outside, but Rayleigh-Taylor instability drives the system to turn itself inside out, and this is a catastrophic failure in this case. So we have to struggle to control these instabilities. If we take a slice through that shell, so I'm going to take a slice through that shell. That's what's shown here. The DT fuel's on the inside, the ablator's on the outside. This is the DT fuel. This is the interface between the fuel and the ablator. You see a lot of Rayleigh-Taylor-like structure developing at the interface of the ablation front, which is the outside of the capsule, where the X-rays are hitting it and driving the thing inwards, and at this interface between the fuel and the ablator. So on the outside of the capsule, we have what's called ablation front Rayleigh-Taylor instability. It scales as the usual type of Rayleigh-Taylor instability that you're familiar with, where k is the wave number, g is the acceleration. Growth rate goes as the square root of that. But because we're ablating the outside surface with X-rays, there are a couple of stabilizing terms that thankfully we can take advantage of. There's a density gradient stabilization term in the denominator here, and there's an ablative stabilization term. The ablative stabilization term is just related to the velocity at which the wind of ablation blows off the surface. The density ablative term, the density gradient stabilization term, is just how rapidly the density drops as you go to larger radius. So we have a chance of mitigating ablation front Rayleigh-Taylor instability by increasing the density gradient scale length and increasing the ablative stabilization. So we actually took advantage of that when we first made progress from the failure to get ignition on NIF in 2012 to something where we shortened the laser pulse and increased the early time part of the laser pulse. We made the Hall realm hotter, we increased the ablative stabilization term, and we stretched out this density scale length. And that's what allowed us to make some initial progress by controlling Rayleigh-Taylor instability on the outside of our capsules. In later years, we recognized that the fuel ablator interface was also becoming unstable. Again, it has a Rayleigh-Taylor-like aspect to it, wave number times acceleration, but it strongly depends on the density jump between the fuel and the ablator. and that we call that the Atwood number, of course. And so now we're trying to engineer this Atwood number to try to minimize the instability at this surface. And now all of these instabilities are basically just buoyancy-driven instabilities. Okay, the asymmetry is different physics. It's not just low mode instability. It is different. So you can understand the physics of why asymmetry matters by abstracting an implosion system to a simpler 1D piston where you have shells of material compressing a hot fuel. And imagine these shells of material have a mass that's different on each side and a velocity where they're squeezing up this fusion fuel. And again, the fusion fuel kind of obeys a PV to the gamma law. So this is almost a freshman physics problem where you can write down energy conservation and momentum conservation for the system. 1/2 mv squared for each piston, 3/2 PV for pressure times volume for the hot plasma inside. Momentum conservation is just mass times velocity. What's happening here is as these pistons converge on the fusion fuel, if you have symmetry, the kinetic energy of the piston is fully converted into internal energy of the fusion fuel. But if you have asymmetry, because of conservation of momentum, there's a net center of mass motion. And in the absence of external forces, once you have a center of mass motion, you have a kinetic energy associated with that center of mass motion, and you never get that kinetic energy back. So asymmetry, at least in this simple translational asymmetry, you give up energy in the form of center of mass kinetic energy. And if you solve this problem, you can figure out that the pressure, again, that pressure is important for us, is related to the mass of the pistons, the velocity of the piston squared, 1/2 mv squared, but it's now reduced by a ratio of the kinetic energy of the center of mass motion compared to the kinetic energy of the pistons that the system had initially. We call this wasted kinetic energy, residual kinetic energy, and it's critical for us because again, if you have any of it, it reduces the pressure. We see this in our data. Of course, we want these to be ideal 1D implosions. They really aren't because we don't have perfect control of our targets. We don't have perfect control of our laser, although we try mightily to control those things. But we see asymmetries in nuclear activation data. We see asymmetries in what we can actually see this net center of mass motion in our data as well. And it's just as actually interesting predicted as the simple physical picture expects. And of course, you can do a more complicated simulation and it gives you the same thing. We have a similar problem in higher dimensions. As I illustrated earlier, our data shows that we have all sorts of non-uniformities or implosions, which is shown here on the lower part of this slide in these neutron downscatter images. This physics of this model of pistons working on a hot plasma can be generalized to higher dimensions. And what you find out is the key metric or is related to the rho r of the system again, but the key is the areal weighted harmonic mean of the shell areal density. And this weighted harmonic mean basically just means wherever you have low rho r, it means you've wasted energy. So if you look at these images here where you have low rho r here, low rho r here, low rho r here, that's a signature of wasted energy. And it's the same sort of wasted energy that just comes from conservation of energy and conservation of momentum. It means you actually desynchronize the conversion of kinetic energy into internal energy. And that's understandable because thick bits of shell have more inertia. They move more, or they accelerate more slowly than thin parts of the shell that have less inertia. And that basically desynchronizes the conversion of kinetic energy into internal energy. And that's what this metric captures. So asymmetry is a geometric reflection of wasted kinetic energy. And that's kind of the upshot. Okay, so energy has been kind of critical, or managing energy in the implosion through managing symmetry and managing instability has been critical to making progress. But actually getting more energy into our targets has also been critical. We needed a little bit more energy than what the NIF was originally designed for to actually get to ignition. Over here on the right, I'm showing fusion yield versus laser energy. You can see our struggles, and there's actually even more data off to the lower left that's not shown, where we struggled to get to ignition, but once we got to about 1.9 megajoules, we started to hit the ignition threshold, and now we're pushing beyond that, and we're trying to get to this plateau of even higher yields, but that's going to require even more laser energy. So we're taking steps at the facility to try to increase the energy delivery capability of the system. That principally involves making modifications to the main amplifier on the laser and the final optics assembly, because we can't just take our system we have now and push more energy through it without destroying the optics. So we have to be able to mitigate uh, debris and other defects in these optics to allow us to put more energy in and get it to target. And there's a lot of work going on that presently at the facility. But once we do that, we hope to access this region up here. Okay, so I'm going to kind of wrap up and maybe take questions by just kind of walking through the different milestones that we've actually achieved. There is kind of a discrepancy between what plasma physics milestones are and what the popular press milestones are. And what I'm reflecting here are the physics milestones, since this is a physics conference. And you have to kind of sort out the popular press milestones for yourself. So, of course, this is the work on the NIF has involved many hundreds of people. On our publications, we actually published for the ignition result, we had 1,370 people who've worked on this for over 20 years, actually over 30 years, the entire professional careers of these people. And it's taken 10 years to go from having a facility to actually getting things to work. So back in 2013, that's the first time we obtained fusion yield greater than the energy deposited into the DT. That's fuel energy gain. A couple months after that, we got what we call alpha heating, which was a milestone laid out by the NNSA, where the fusion yield was doubled by this alpha particle self-heating process of thermalizing the alpha particles, increasing the temperature and getting the yield to go up. That was in January 2014. A burning plasma, which is the same as the magnetic fusion definition, where the heating of the plasma, the self-heating of the plasma, exceeds the external sorts of heating. That was obtained in the NIF in 2020. Ignition, which is the Lawson criteria threshold for the tipping point of thermodynamic instability. That was obtained on August 8th, 2021. Scientific break-even, which is where we have more fusion energy coming out than what was put into the target, not more than was put in by the facility, but more than was put into the target. This was obtained December 5th, 2022. This is the one that's kind of often misstated as ignition, but it's actually target energy gain or just scientific break-even. And then net energy gain, which is another one some of the press has gotten wrong. This requires us to get more fusion yield out of the facility than we put into the facility. But again, we put in 327 megajoules of electrical energy into the facility. This has not yet been demonstrated, so it's important to kind of be clear on that. Okay, so with that, I'll wrap up and I could take questions.